It's great to be here, and I'm joined here with Bill, one of the team leads at Geoscience Australia. We're going to be talking about operating mission-critical applications to help citizens in the face of national disasters. So this is a Voice of the Customer session, so you're not going to hear that much from me. But I'll just give a quick intro around some of the principles of architecture on AWS and talk a little bit about our well-architected program. So if you've been to an AWS talk that's discussed architectural principles, you've probably seen these sort of 7 points put on a slide. And these are some of the key points that we've highlighted to a lot of our customers and that we've found useful for them to think about when building high-scale distributed systems in the cloud. So the first one here says design for failure, and it's important, and nothing will fail. So you shouldn't be designing your system to fail, but what you should be doing is thinking about all those failure scenarios that can happen in a system and actually get rid of those, get rid of single points of failure, think about what happens in different types of scenarios. And that can be an iterative process, so you might not get it all correct up front and may take time. Secondly, building security in every layer. So if you're used to a traditional world, you might have relied on, say, your boundary firewalls, your DMZs, and then not worried about security inside. The cloud, we offer a much more finer-grained and secure posture there. So even right down to individual servers controlling what traffic can go in and out of those. And the third one here is around leveraging different storage options. So in the traditional world, you might have been used to, well, we bought a SAN, we spent $1 million on it, therefore that's the solution to all my storage problems. In the cloud, there's no upfront cost required. You're free to choose different options, even at a project-by-project basis. So that means you can choose the right option for the project at the time. So a lot more flexibility. And then implementing elasticity. So this is really important for a use case like we're going to talk about today that needs to scale up rapidly in the face of some sort of event. But even for other applications in government, say if you launch a policy initiative and so on, where you get a lot of customer interest, or in a federal election scenario where we've worked with customers to help in those type of situations. But as well as scaling up to meet load, you also want to be able to scale down to save costs. And again, that's something to think about in your architecture. And then looking at parallelism and thinking, can you take advantage of parallelism to help in your architecture? Often people are used to just single servers and serial processing. In the cloud, you might have had a workload that, say, took you 8 hours to run on one server. You could still do that in the cloud, but you're free to say, I'll run 8 servers for 1 hour, and the cost is the same in both cases. But the time to results is 1 hour versus 8. And then think about loose coupling. So this is think about asynchronous processing, decoupling parts of your system. Because if there is a failure in one component, the rest can keep working. And you can also give customers a better experience. It's a much better experience to say, send me some data, and then I'll let you know by an email when it's ready, rather than saying, send me some data and wait till I've got the result for you on a web page. And then finally, think about don't fear constraints. So often in a traditional world, you might be used to only running things in a server and only having these particular options. If you come to an environment like AWS, you've got a wealth of, say, server sizes and different options you can put in place. You can leverage parallelism to get around limits on single server sizes, but you can also use completely different paradigms. You can move to containers very easily, move to serverless Lambda processing and so on. And you'll see examples of some of these in this talk today. One of the programs we offer to help customers when they are architecting solutions with us is what's called the Well-Architected program. So if you go to our website, you'll be able to find a wealth of white papers and material on this. And this goes through these 5 pillars. So we work with customers around their operational excellence, making sure they've got best practice security in place, diving down on things, are they building a reliable system that responds well in the case of failure scenarios? Are you making the best performance efficiency trade-offs and using the right service for the job? And have you cost optimized? So we actually spend time helping customers save money on the platform, say with different pricing models or different architectural choices. So that's just a little bit of introduction of some of the programs we do around the architecture space, but I want to leave all the time now for Bill and to talk about the earthquakes at GA website.
Okay, thanks for that, John. Hi everybody, my name is Bill Farmakis, and today I'm going to talk to you about a journey to the cloud and getting Earthquakes GA on AWS. So my team's called the Flying Hellfish, and we're a team of 7 software developers. I'm the tech lead iteration manager, and of course my biggest passion, which is software engineering. So Geoscience Australia is responsible for monitoring, alerting and reporting on significant earthquakes to alert the government and the public. Now, Geoscience Australia has 4 mission-critical applications: Earthquakes at GA, Tsunami Warning, Nuclear Monitoring, and Sentinel. Now, Sentinel is GA's bushfire monitoring application. So Sentinel was our first mission-critical application that went to the cloud, and with great success. So the last 2 bushfire seasons, we had 100% uptime, and we saved the cost of about $85,000 per annum. So in saying this, we had great confidence in AWS, as the products work really well, the documentation is excellent, and their customer service is second to none. And to mention Sentinel, the last bushfire season was on-premise. We had 5 major outages, and the Earthquakes website, when it was on-premise, it used to crash every time we had a major event, so not really ideal. So Geoscience Australia runs the Earthquakes Alert Centre, and this is run 24/7 and always has at least 1 seismologist on duty. So when an earthquake occurs, it's picked up by ground stations around the world. There's over 200 of them. They're beamed up to a satellite, they come back down to GA on-premise, and then they're pushed up to the Earthquakes Alert Centre. So this is where the seismologist comes into play. They'll review the seismic data in the XML, and if they're happy with the data, they'll publish it, and then you'll end up on the web application that you see down the bottom. So this will be the component that we'll be focusing on today. Now keep in mind that the Earthquakes Alert Centre AWS system and Earthquakes at GA were both put up in the cloud in late May, and they went up together in parallel. So now I'll delve into the architecture of the system. So don't feel too daunted by this diagram, as I'll break down the components and I'll explain why we use them. Now, another thing to keep in mind is when we first started out to design this application, we didn't come up with an architecture diagram. We actually drew the diagram right at the end of the process, so about 1 week before, as it was constantly evolving, and I'll explain a bit about this a bit later. So first I'll start off with the user interface. So a user comes along, they hit earthquakesga.gov.au, and then they hit Route 53. Now Route 53 handles your traffic routing for you, and then it'll route to CloudFront. So basically what CloudFront's for, it distributes your content to edge locations around the world. So basically when a user hits your site, there's lower latency, so it's faster performance. And then you have S3, which is Amazon Simple Storage. So we try to use as many open source products as we can. So the user interface is built with Angular, and the mapping component is using open layers. Now, when the application is built, it's stored on S3 as a static content. So, and then it's hosted as a website. So there's no servers involved in this process. Now, why have we done it this way? Well, you basically get the same uptime as S3. Another advantage is the cost of this is about $50 a month, so it's pretty cheap to run. Another advantage is if there's a problem with the web services in the back end, your website will still come up, you still get a map, and let's say you hit the recent earthquakes tool, the panel will open up and you can display a user-friendly error message. So gone are the days of ugly stack traces. So next I'll talk about how do we actually get the data onto the map. So how do we get the earthquake points onto the map? So for this we use GeoServer, and basically GeoServer lets you create OGC compliant web services off the spatial data in your RDS or your database. So in the diagram here, on the left-hand side up the top, you can see was the slide I showed you before in the user interface. So CloudFront here is distributing static content. Now we're going to move to dynamic content, which is on the right side. So you see CloudFront talks to our application load balancer, which is inside our virtual private cloud. Now, our application load balancer, its responsibility is to distribute traffic to the EC2 instances. Now, you notice here that each EC2 instance, there's at least 1 in each availability zone. So there's a minimum of 3 running all the time. Now, this is done for redundancy. So each EC2 instance has a single instance of GeoServer running on it. Now, if you look down a bit lower, you'll see the RDS, which is our database. Once again, we run it across 2 availability zones. So there's a master and a slave. Again, this is done for redundancy. And just under that, we have the auto scaling groups. So the ASG basically allows you to set policies on when you want to scale up. So for us, we look at CPU when it's at 80%, and when it's there for 2 minutes, we'll scale 2 servers. Now, we scale it kind of aggressively, because you've got to remember that it takes 1 or 2 minutes for a server instance to come up. And on the right side, also the ASG is also responsible for health checks of the EC2 instances, and if it finds one of the EC2s is unhealthy, it will terminate it and start a new one. Now, we can scale from about 3 to 10 servers is what our scaling policy is. And you also put your cool down policies as well, so when you want to scale down. Now on the right side, you have the AMI. Now the AMI is the Amazon machine image. This is basically a master image for when the EC2 starts up. It will grab this image and it will start with that. So in our AMI, we have baked in GeoServer, and we have other things like CloudWatch alarms. So the more things you get in the AMI, the less it's got to do when it goes to start up. So one of the key features of the Earthquakes at GA website is the ability to submit felt reports. So basically, when a user feels an earthquake, they can jump on the site, they can fill in a quick multiple choice form, and then submit it. Now, the seismologists will use this to analyse the felt reports against the real earthquake. So the blue dots on the map, they represent clusters where users felt an earthquake. So if you jump on the site later, not now, later, if you jump on the site later and zoom in, you'll see the clusters break down and you'll see exactly where the earthquakes occurred. Now, this is where serverless comes into it. So for this component, we use AWS Lambda. So basically, AWS Lambda lets you run code without having to provision or manage your own servers. So you're not paying for idle time. So if you look here, the user comes in, they fill out a felt report, they submit it, and it will go through, and it will hit api.earthquakes.go.gov.au. So that will traffic through to API gateway with a secure key, because to talk to the API, you've got to have a secure key. API gateway will then trigger Lambda, and Lambda will then write your felt report into the database, which you can see on the right side, which is the RDS. Now, Lambda can run multiple languages, and for our purposes, we use Node and Lambda. So Node and Java. So we use Java for the more complex parts we want to run. We also use serverless for things like our RSS and Atom feed generators. We use it for our email subscription service, and we also use it for our CloudWatch notifications to Slack, which I'll talk about a bit later. So this is the last architecture diagram I'll run through. So on the left side, you can see the Earthquakes Alert Center AWS account, and on the right side, you can see the Earthquakes at GA AWS account that my team look after. So like I said before, seismologist comes in, they'll publish an XML file, and it's dropped on an S3 bucket. Now the S3 bucket will trigger the simple notification service and publish a message. So on our side, we have the subscriber, so it's subscribed to the topic. So our simple notification service is sitting there listening. It says, yep, I've got a message come in, I'm going to put it on the queue, which is our simple queue service, SQS. Now, it will sit there on the queue until the Earthquakes Process application, top right, will pick it up. So the Earthquakes Process application is a Java application that basically parses the XML file, and it does some other things like calculate the epicentral time of the earthquake, and then it will write the information to the database. So there's one instance of the Earthquakes Processor application on each EC2 instance. And they will sit there listening, and only one of them will pick it up off the queue, process it, and put it in the database. And you also notice up the top we have code deploy. So code deploy we use to deploy our Earthquakes Processor application to each EC2 instance, and it will do that one at a time, making sure it's successful before moving on. So next I'll talk to you about load testing. So we load tested 20 million users hitting the website in over a 1 hour period. So we use JMeter for our load testing. We used 5 M4 large EC2 instances. We used 1 master and 4 slaves. Now we did this for I/O, for purposes of I/O. So CloudFront was getting hit 1,500 times a second, and we transferred 965 gigabytes of data. And the table at the bottom, you can see the response times. So 90% of the requests came back in 69 milliseconds, and 95% of the requests came back in 77 milliseconds. So this is pretty phenomenal performance coming from CloudFront. And the cost to do a test like this was about $250, and it's pretty much invaluable. And you'll see why in the next slide, why it's so important. So this is the good news story, right? But when we first ran this load test, we had 100% CPU on the database in about 3 minutes. So at this point, things weren't looking good because this was about 2 weeks out from production. So what we ended up having to do was we ended up having to do some performance tuning. So the disk size on the RDS, I think it went from about 20 gig to 150 gig, because Postgres relies on this. We also did some performance tuning of the system parameters inside Postgres, so things like auto vacuum and page cost. We looked at tuning the connection pool size for GeoServer, and even the Java virtual machine parameters for when GeoServer starts up on the EC2 instances. So once we've done all that, we got the results you see here. So everyone's on the serverless bandwagon, right? So I'm going to break the bubble a bit here. So we found it's excellent for tasks, guaranteed to run for less than 5 minutes, and your performance expectations must be taken into account. So we were processing XML files from about 10 to 50,000 lines long. They were processing in about 2-3 minutes, and things were going well. Now, a week out from production, the business decided to send through an XML file that they hadn't before. That's 300,000 lines long, and Lambda times out. So at this point, we're like, this is not good. So what we ended up doing, because we had done our load testing, we knew we had the capacity on our EC2 instances. So what we did, we installed Tomcat on there, packaged the WAR file, deployed it on there, and it ran in 35 seconds. So this kind of gave us a baseline. So for our needs, Lambda didn't suit for this particular function as well, and the business had said the processing has to be under 1 minute after they discovered that it failed in Lambda. So we ended up having to do a re-architecture, and it only took 1 day. So this is one of the best things about AWS and cloud. You can grab a component, if you built a good architecture with loose coupling, you can rip it out, it affects nothing else in the system. You can move it onto the EC2 like we did, and within a day, you've changed the architecture and it's running perfectly as expected, meets the business expectations. So this is a graph of CloudFront Statistics for the month of August. So this is everything hitting CloudFront. It's not just the user interface. This is your API calls, your RSS feeds, Atom feeds, everything hitting it. So you can see on most days you're doing about 250,000 to 300,000 hits. Now you can see August the 8th, there was I think a 3.3 in South Australia, and there was a 4.3 and a 2.4 I think in Western Australia. So you can see it spiked to 900,000. So this is where cloud's very important. Your scalability and everything like that, because you just don't know when an event's going to happen and you want it sitting there. Now, if this was on-premise, you'd have to build a system that would have to support that kind of capability, and you'd be running those servers all the time, which is a waste of time, because look, it happens 1 day of the month it happened, that's when you need that capacity, and that's when it's scaled up. So you would have heard about the ASD Essential 8, and this is what we're doing with this application to mitigate the risks. So for application whitelisting, we're using continuous integration and continuous deployment for consistent and reliable deployments of the applications. For number 2 and 6, we're using AWS Patch Manager. So basically, we set patching to run every night, and you can set your own severity level to what level you want to patch to. Number 5, restricting admin privileges. Now, this one's pretty important, and we take it very seriously when it comes to security. So write your own custom IAM policies. Don't put action star in there. So for your EC2 instances, you should be saying, you should put a deny clause in there saying you're only allowed to run M4 large EC2s and nothing else. It's all about risk mitigation. So IAM as well, if you put IAM star, IAM has 158 actions in there. If your account is breached, they can change your password and lock you out of your own account. This user here that Earthquakes is using only requires about 10-20 actions out of IAM. So try to restrict it as much as possible. And again, minimum privilege. All your users in the system, make sure they only have the permissions they need to do their job. Not everyone needs admin access. We also do multi-factor authentication for anyone with console access, and we do database and EBS snapshots on a daily basis as well. So some other security considerations to take into account, AWS Guard Duty. I highly recommend turning this on as it's intrusion protection, and it cost 94 cents last month to run for Earthquakes. So it's cheap insurance. AWS Key Management Service. So you can create encryption keys and you can set them to automatically rotate. So basically the encryption keys we create are for API gateway, they're for our S3 bucket, and then for encrypting our database, just to give a few examples. And for the next one down, which is the parameter store. So AWS Parameter Store lets you store things like your database credentials. You can store them there with an encrypted key, and they need this key to be pulled back out. So when an EC2 instance starts up and GeoServer needs to be configured, it will go to Parameter Store and it will pull the user credentials out for the database, install them in the config file, and then start up. So they're stored in one central location. They're not in a repository somewhere. They're in a safe encrypted place. And for Bitbucket pipelines, we use encrypted environment variables. So you need your AWS deploy users, and they're encrypted in Bitbucket pipelines. So another commonly overlooked aspect is repository documentation. So we at least put an image of what the app looks like when it's running for the next developer that comes along. We also put what it is, how to build it, deploy it, test it, and who do you talk to if you have a problem. So we also tried to apply separation of concerns to our repositories as well. So Earthquakes, the user interface, Earthquakes UI has its own repo, Earthquakes Lambda has its own repository, Earthquakes AWS. Now this one's used for our infrastructure as code, which I'll talk about next. But it also has things in there like our runbook, our disaster recovery plan, and yeah. So I spoke about infrastructure as code before, and for this we use Terraform. So Terraform basically gives you version control over your infrastructure. So it allows you to have consistent configuration across all your environments. So the example I have here is for our Jumpbox. Now Jumpbox is basically a Bastion host that lets us access our private EC2 instances from inside GA's IP address. So configuration is there that Terraform is required to run it, and when you run this, the output is a Jumpbox that has been built, which is the image at the bottom, which is in the EC2 dashboard. And another thing that Terraform allows you to do is it allows you to run plan, which allows you to show you what the execution would look like without actually having to apply the changes. So for Earthquakes, 95% of the stack is in Terraform. So the only time you're going to the console to make a change is never. Only initially when you have to set up the user for Terraform. So you've got to set up DynamoDB. You have to set up an IAM user, IAM policy, and an S3 bucket. And that's the only time you'll make a change. And the rest is in there. So yeah, it's all about consistency across your environments. So I intended reinventing Las Vegas last year, which I highly recommend. And in between all the casino sessions, I actually managed to attend some talks. And I went to a talk called Tools Won't Fix Your Broken DevOps. I highly recommend you check this out on YouTube. They spoke about some great things, which included high-performing teams, culture, and the inefficiencies of CAB. Now, I'm not a big fan of CAB, never have been, as I don't think it adds any value to the software or the organization, and it definitely doesn't improve the quality. Can I get a show of hands who still has to use CAB to go to production? That's some people, that's improving, that's good. So I'll show you what I've come up with here. So on the left side we have our branches. In the middle we have our Bitbucket repository where we store our source code. And next to it we have Bitbucket pipelines. Now Bitbucket pipelines, it will run a custom Docker image that we've built. And it has things in there like the AWS command line client, it has Node on there, it has Chrome headless on there. So we require Chrome headless to run our unit testing as it does testing on the browser. And the pipeline, when it runs, it will also do the Angular build, it will also do our unit testing, and it will do our static analysis. So we're pretty strict with the quality of code that comes out. If there's a single space or a character in there, the pipeline will fail. So a day in the life of a software developer in my team, you create a feature branch from the develop branch. Once a developer has completed their work, they'll create a pull request from feature to develop. Now this requires one other team member's approval. Once they have this approval, it's a single click which will automatically kick off the development pipeline. Development pipeline will kick off Bitbucket pipeline, so it'll do the build, the unit testing, static analysis, and it will automatically deploy to the non-production AWS environment. So we have two AWS environments, production, non-production, they're both split. Now to go to production, the developer will then, there's a couple more steps in this one. So from develop to master, you raise a pull request again, but this time you require at least 2 team members, other than yourself of course, to approve it, and also the business owner. Now at this point we use Jira for issue tracking, so the business owner would have gone through, tested the changes in non-production, and they would have said, yep, I'm happy for this to go to production. So once you have all 3, you hit the merge button, again kicks off the master pipeline, and it will run exactly the same pipeline that it ran before, only this time it's pushing to production. So this is really efficient process. It keeps the team happy. You have the right level of governance, so it's not too heavy. Also, the pipelines take about 5 minutes to run. So we've done 51 deployments to Earthquake since we launched it in May with 0 rollbacks. And if we did have to roll back, it's 5 minutes. You just find the last successful pipeline for that branch, run it, and you've rolled back. So it's a pretty good process. So I spoke about unit testing in the last slide, sorry. And for earthquakes, we have 92% coverage, and this is a report that Angular produces when you run code coverage. Usually unit testing only covers things like your JavaScript components, but we test all the HTML components as well, form submissions, button clicks. This is all to ensure a high quality code base. So next I'm going to talk to you about cost saving with reserved instances. So I've been to plenty of these talks and people say, yeah, it's great what you're doing, how much does the thing cost? So if you focus on the graph at the bottom, you can see the RDS and EC2, so your database and compute, is where the majority of your cost is. So AWS have the ability to purchase upfront reserved instances at a discount. So for our EC2 compute, you can see if it's unreserved, it will be about $6,000. If you reserve it for 1 year up front, the cost comes down to $3,000. If you reserve it for 3 years up front, the cost comes down to $2,000. So you can start to see the cost savings coming in. With the RDS, because the RDS is multi-zone, it runs across 2 zones, it costs a bit more, it's $14,000 unreserved. If you reserve it for 1 year, it comes down to about 8. If you reserve it for 3 years, it comes down to 5. So the stack over the year is about 20K. If you reserve EC2 and RDS, it comes down to about 13K. If you reserve it for 3 years, it comes down to 9. So over the lifespan of 3 years, which is app is pretty much guaranteed to run, the stack will cost you $60,000, with reserved instances comes down to 27. That's a massive cost saving, especially when you're working in government. So because our team does DevOps, we build it, we operate the app as well, so we're responsible for it. We set up CloudWatch alarms. So basically CloudWatch alarms, when one's triggered, it will call Lambda, and Lambda will post to our DevOps Slack channel. Now this is all about getting communication to the right people at the right time. So the Earthquakes Alert Center is subscribed to this channel, and so is my team, of course. So what are things we're monitoring? We're looking at EC2 and RDS, 80% CPU memory and disk space. We look for Lambda timeouts. We look for Lambda concurrent executions, as you can only have 1,000 per account by default. We look for any application errors, so Lambda, Java, or GeoServe errors. You can actually pull the error out of the log, and you can actually post it to Slack. Now the application load balancer host health, that one wasn't there in the beginning. Now I'm not going to get up here and say that everything was perfect, everything ran perfect, we never had an outage. So we had a minor outage, and what had happened was AWS Patch Manager had done a kernel update and rebooted instances. What's the one thing we didn't test? Reboots on the instances. We tested manual terminations and that kind of stuff. So what we ended up doing was I jumped on the console, had a look what the problem was, and after being contacted from the business area, terminated instances, they came back up because when you start an instance from scratch, the startup script's there. So the first thing we did when we got into work the next morning was we added this CloudWatch alarm in, and we added the add reboot cron tab, we added the startup for GeoServer. So the lessons learned, as John was talking about earlier, was the well-architected reviews. They provide invaluable feedback. So we did them about a month or two before production. We got feedback, and we applied changes like CloudWatch alarms for concurrent Lambdas, and it also provides feedback and lets you know if you're doing the AWS best practice as well. So definitely the importance of load testing. As you can see, it allows for future enhancements and changes. You know whether you have capacity or not and what the system's going to handle. Don't expect things to perform out of the box. Always allow time for performance tuning. And the best thing about cloud is you can experiment and fail quickly for a reduced cost. So that's all from me. I want to thank you for your time, and now I'll hand you back to John.
Great. Well, thank you, Bill. We've got a minute to go, so there's time for a couple of questions if people had something to drill down with Bill. So any questions? We've got a mic that we can give out if people need that. Just down the front here.
Hey Bill, just wondering if you thought about using Spot for your processor instances, and if so, what made you choose reserved over Spot in that case?
Reserved instance is, it's not actually reserved to Spot. Spot's not. Like,
Yeah, so
I think-
spots where you can bid for an instance. So I guess in this case you wanted some guaranteed
want-
capacity.
Yeah, it's got to be 100%.
Yeah.
Yeah,
It's
okay.
got to be there 100% uptime. That's
Yep.
the difference.
No worries.
Yeah, so actually I think that came up in the review. I mean, one option there would be potentially you might want to use reserved for your base capacity, so those initial 3 instances, but you could potentially use spot or on demand for instances when they scale up. Any other questions? I think we've got maybe one more, and that's, yeah, there's just one more in the middle there.
G'day, Bill. Why Terraform and not CloudFormation?
That was driven by our cloud team. So, yeah, so we're kind of following the agency patterns that were put out by our cloud team. So that was basically the direction we took.
Great. Well, thank you for your time, and please give us feedback. We use that to improve these sessions over time. And let's give one more thank you for Bill.